Good afternoon again. My name is Kostas Papas. For those that do not know me, I'm the Assistant Director of the Texas A&M Energy Institute. Welcome in person and through to the special international energy seminar that organized by our institute late Friday afternoon, and I really appreciate your participation. It is for great honor and respect that I introduce you, Dr. Papadakis, the Professor of Renewable Energy Technology at the Agricultural University of Athens in Greece. Dr. Papadakis, together with a group of 10 amazing students from the university, are visiting us in the framework of a project that is sponsored by the US Embassy in Athens and is focusing on the study of energy transition impacts, societal impacts of energy transition. The 10 students from the Greek University are collaboratively working with 10 students from the Texas A&M Energy Institute. Most of them graduate students, PhD students, and master's students. They meet regularly, working on 5 topics that they have pre-identified. And the progress that they have done is amazing. And with this trip to College Station, they had the opportunity to meet each other and advance more their progress. So in the framework of the METAVASIS project, Dr. Papadakis will present to us a very interesting topic on desalination, but I would like to share with you a few details of his impressive bio. I had the honor to work with him back in 2009 until 2012 when I was under his supervision. At that time, he was the vice rector of the university, and I was the administrative head of the research committee of the university. So we had a daily collaboration. After that, this collaboration turned to a friendship, and we are really happy that we are hosting him today. Dr. Papadakis' research interests are mainly focusing on sustainable agriculture and renewable energy, including bioenergy, photovoltaic systems, microgrids in agriculture, and remote areas. Water desalination, of course, combined with renewable energy and heat and mass transfer in farm buildings. Since 1996, he was the principal investigator in more than 35 projects, multi-partner international projects funded by the European Commission. He cooperates with public and private organizations from more than 35 countries in Europe and internationally. And he has successfully supervised numerous PhD students. Currently, he supervises 4 PhD students. And a very important component of his impressive bio is the fact that since 2020, he is in the top 2% of seated researchers internationally in the field of energy. With this, I would like to give the floor to George Papadakis, and I would like you to welcome him with a loud applause.
Thank you, Kostas. Thank you very much. The pleasure is all mine, and it's an honor. All mine. See, I'm really honored to be among you and asking of the Texas A&M University. We have, as you heard, we know each other, Kostas, for many years. We are good friends, although we are not close anymore, physically close, I mean. But we finally did it, and we got this project now. Closely collaborate. We have the opportunity to visit the university with the students, and also American students will come to Athens in March. So our research is mostly focused on renewable energy in agriculture and remote areas, many forms of renewable energy, and we try to promote the application of renewable energy with many systems. Among these systems is systems for water desalination. And mostly we have been working with reverse osmosis, and I will explain in a minute why. Okay. Why renewable energy and seawater desalination? Because it's very attractive to reduce dependence on fossil fuels and CO2 emissions. Renewable desalination today can be cost competitive with fossil fuel desalinations, but especially on islands, but also in many other places in the world that face high cost for imported fossil fuel. The cost of water on islands can be reduced by running desalination system based on reverse osmosis, mainly because reverse osmosis has low energy requirements per unit volume of fresh water produced in comparison to thermal methods. As you can see on this slide, there are many.
It doesn't show on the TV.
Anyway, you can see the, except from the blue color, you see how many other areas in the world suffer from water scarcity. So you see Mediterranean here, North Africa, of course, the Arab countries here, but also other areas, including United States, in the south of the United States, and also Australia. And the problem is becoming worse and worse as the years passing, and also due to climate change. Now, let me explain in more detail what was the motivation somewhat 15 years ago for us to work with desalination in combination with renewable energy. So this is Greece, part of Greece. These are islands in the Aegean Sea, many islands. The numbers here are from 2015, if I remember well, and these are cubic meters per day of desalination systems installed in the islands already. Now there are more and more. Now, what's the problem there in the islands? The problem is that the islands, most of the islands, even today, are not connected to the mainland electricity grid. This means that the islands receive a huge number of visitors during the summertime. So you may have an island with 1,000 inhabitants during the winter time, and in summertime, in just 2 or 3 months, you may have 10,000 visitors. So you have high power demand and high water demand. And how to satisfy this? The water resources existing on the islands are simply not enough to satisfy the demand of water during summertime. And this is not only the case for the Greek islands, but also in many, many thousands of islands all over the world. Even in the north of Europe, I learned that in an area between Norway, between Sweden and in this area, they are still, even there, they start desalinated water. Even there, they start desalinated water. So how to provide water in a sustainable way in these islands, and how to combine the energy-intensive process of desalination with the power demand, especially during the summertime. A couple of years ago, we participated in a study made by the European Bank for Reconstruction and Development, and the focus was actually on small systems up to about 2,500 cubic meters a day to satisfy needs of such small islands and coastal communities all over the world. But we focused mostly on Mediterranean. So parts of this study I'm going to present you today, but also I'm going to give you the results of our experimental work and also some perspectives for the future regarding the combination of renewable energy with reverse osmosis mostly. Just a few words about desalination processes. There are thermal processes, membrane processes. The well-known and already applied for many years ago, already implemented for many years ago, MSF distillation, and the distillation principle is, of course, the way of working with thermal processes and MED. Hundreds of thousands of cubic meters a day are still produced, fresh water are still produced in the Gulf and in many other areas, mostly in the Arab countries, with these methods, but not anymore. Because today, the major process the new systems installed in several areas in the world is now the reverse osmosis one, mostly. And I will explain why. There are also some other processes, but I'm not going to discuss about that. Just to explain what is reverse osmosis, you probably know about osmosis. Here, pure water goes through a semi-permeable membrane to this side, where the concentrated solution is. But if you apply a pressure on this side, then you have the reverse process, and then water molecules pass through the membranes to the other side. And in this way, you produce fresh water while you have concentrated solution left on the other side. So this is what we do with reverse osmosis. And of course, you need pressure, it means energy. So you have to overcome the osmotic pressure so that to produce fresh water. So that's a typical arrangement today of a reverse osmosis system. You have the feed here, feed pump, and then the high pressure pump here. Well, I will explain more about this system here, because this system is a very clever system that developed just something like 10, 15 years ago, so-called pressure exchanger, so that to reduce the energy consumption of this system. And this is the membrane module, and you have the saline water here, seawater, for example, and then on the other side you get the fresh water, while here you get the concentrated brine, which is of high pressure, still of high pressure. So you use the system to get some, or most of it, or most of the energy contained in the brine to recover And this way you recover energy and you reduce the overall energy consumption in the system. Of course, there are also other processes associated, like feed pretreatment or post-treatment of the water. Mostly chemicals are here, but it's not our scope to discuss about this today. So as I mentioned, desalination is an energy-intensive process. So you see here the energy consumption kilowatt hours per cubic meter. When you want to produce 1 cubic meter of fresh water, while you see if you get water from a lake or groundwater, you need some pumping here, or wastewater treatment and reuse. You see how low is the average energy consumption. So if you have water resources, it's foolish to go to desalinated water because its cost is too high. Now, how we manage to reduce the energy consumption specifically for the reverse osmosis systems? There are several systems developed and used today. The first system to recover energy was the system of Pelton turbines, but later on, something like 15 years ago, we have the development of several volumetric systems like the Clark pump that we have been working with, a small system in the laboratory, the pressure exchanger that I showed you before, and the latest system is this axial piston pressure exchanger pump, which is also working very well and managed to reduce the energy consumption quite impressively. Now, this is the operational principle of the hydraulic energy recovery. This is the Clark pump. So you have the membrane, you need high pressure, and then you get the brine, which is also of high pressure. Let's say that you have here 70 bars. Here you will get something like 68. And then this high pressure is used to move this piston. And in this way, by using this piston, two-way piston as you see, you actually help provide energy to the feed water to drive then again the salty water, the feed water to the membrane. So in this way, you recover a lot of energy contained in the brine and you reduce the overall energy consumption. It was a patent by this company at that time for small systems, for yachts, for example, or domestic systems. And then a couple of years later, this pressure exchanger system developed, that so-called PX, which managed to reduce the energy consumption down to 2.4, 2.10 kilowatt hours per cubic meter. And that was a big revolution in the desalination technologies at that time. This system still, of course, exists, commercially available, and in many systems, this PX exchanger is installed. Just a few words how this system works. So you see the ceramic cylinders here. You have the low pressure and the high pressure, blue and red. And this chamber rotates. And it rotates so that to bring several openings in line together. So when a low pressure feed water fills the, then it displaces the brine like that. Because it has high pressure here, it was locked inside there. And when this opening is open, then the other water, the brine water and the feed water enters here and it throws out the water. So this system works very efficiently, very clever system, and With this system, the energy consumption reduced, and another also very smart system is this one, where you have the high pressure pump, which is on the same axis with a similar pump, very similar pump. This is positive displacement pumps, and the one works as a pump and the other one as a turbine. So you get the concentrate here, the brine, and it actually, it's the same principle, helps this pump because it gains energy from on the same axis here to pump the water towards the membrane. And here you see in the several years, the impressive reduction of energy consumption in the reverse osmosis systems, especially here in this area. You see how low we are now, below 2, the system itself, below 2 kilowatt hours per cubic meter, not the overall consumption, because you have several accessories and also some other apparatuses that consume energy. But the system itself today, we managed to go down to below 2 kilowatt hours per cubic meter. And if you compare this consumption with other technologies, you see that the membrane technologies, reverse osmosis, is now one of the lowest, has the lowest energy consumption. And this is the reason why practically all new systems installed throughout everywhere in the world is now reverse osmosis. Another advantage of the technology is that it is modular. So you may install a small system of, let's say, 1 cubic meter a day for a house nearby the sea, or you can have a very large system of 50,000 cubic meters a day by adding modules, more and more modules. That's a big advantage. Now, regarding the combination of reverse osmosis mostly, or other technologies, desalination technologies with renewable energy, there have been many trials, research trials and demo trials. Many pilot systems have been installed and tested all over the world, trying to combine thermal technologies with many different renewable energy technologies and sources, like, for example, geothermal energy, of course, solar energy, but not only electricity production technologies like photovoltaics, but also thermal technologies in combination with thermal technologies, but also other, like the vapor compression. However, after all these research and demonstration trials, it seems that photovoltaics or wind, and specifically electricity production technology renewable energy technology seems to be the most appropriate for providing power to reverse osmosis, which is now the dominant technology in the world. Nevertheless, when you have available geothermal technology or another source of heat, free heat available, as Professor Hassan mentioned yesterday, then of course you have to consider other technologies other than reverse osmosis. Now, this is a typical layout of a combination of PV and RO. We have the panels, we have a battery charger. You may charge the batteries, and then you have the inverter, and then you have the loads. And this is a typical system. I mean, this part is really typical. It's a typical autonomous photovoltaic system, and you combine the load, which is a reverse osmosis system. So this is nothing innovative about that. But it has been used today in many places in the world. This system is implemented, as you see, for small-scale systems in many places in the world, autonomous systems, not connected to the grid. In the laboratory, we have been testing photovoltaics and small wind combined with or we could have all kinds of combinations here with DC motor or through a pump clock for energy recovery to test the reverse osmosis system. But we have also participated in several research projects in many places in the world, including Europe, but also North Africa. This system, one of the first systems installed some 10 years ago for brackish water, not seawater. This was inland in a village in Morocco. And you know what is the problem there? The problem is how to treat the brine. If you have a system nearby the sea, there's no problem. You just return the brine to the sea. Of course, there are several standards how to do that, and knowledge how to do that, not to have any impact on the environment in the sea. But generally, there is no problem when you get rid of the brine in the sea. But here you do have problems. So this is still an unsolved problem for large quantities of water. So when you combine the PV with RO, still batteries are expensive. And if you want to lower the cost of fresh water, you might think that you want to get rid of the batteries. So we started doing tests with a battery. So this is solar radiation intensity is the blue, PV power for small system. And this is the motor power of the desalination system. And you see that it's simply, you provide all the energy by the battery. So you don't care. If you have enough battery, just provide enough power and energy for the system to operate even for 24 hours. But the idea is, okay, let's suppose that you install a reverse osmosis system without a battery for the photovoltaics, and you pump the water that you need when the sun is available. So you store water instead of storing electricity. That's the idea. Then what will happen? It's inevitable that the motor power will follow the available power from the PV system. So you have this kind of variations in the operation of the system. And you see also here that the inlet membrane pressure also varies and follows practically the available power from the system. This is, according to the membrane manufacturers, this is not good for the membrane. But nobody has proven it. Nobody has proven that. And Vangelis is still working on that with some cells. He didn't give many details during his presentation, but nevertheless, you can discuss more if you are interested in this specific matter. Now, there are also other issues when you don't have a battery. The system starts late because there is not enough power in the morning to operate the motor, and also during the sunset, late in the day. And as you see here, the motor is going to operate at a certain point of the day because you will get the motor will get the power it needs, the nominal power. It will operate at the nominal power, and you will have some energy that is lost during the daytime, during that time. When you have a nice sunny day, you will have more power available than required by the motor to operate. So you have to do something about that. And what we thought is to include a kind of buffer, just kind of buffer for the system to operate. So we actually tested an electrical buffer, but we didn't use batteries, conventional batteries at that time, lead acid, but we chosen to use hybrid capacitors with small storage, so that exactly to smooth out these fluctuations, and also a hydraulic pressure buffer with pressure vessels, and develop a special control system to operate the reverse osmosis system at the optimum point, depending on the energy available from the system, from the photovoltaic system. This is the layout anyway. And this is then the combination that we used along with the control system. I will give you some more details about that. And anyway, this is the electrical layout of the system. There's nothing, not very normative. This is just to help the system to operate. These are the pressure vessels, 16 bars, minimum pressure 4 bars. And this is the original electrical storage that we developed. These are the capacitors, very small storage, just 0.6 watt hours for the small system we had. And this is the control system that was developed by another PhD student. Quite original for its time. You see that the action is to determine the operation point of the seawater desalination system. And Vasilis is working now more on this system for another purpose, of course. And we have used computational intelligent algorithms. So the several agents, the PV, the water tank, because you remember that the idea is to store the energy, the available energy in a tank, in water, and provide that water during the hours that there's no sun, there's no energy. And with this system, we managed to operate the system in a very effective way, I would say. So I give you some results shortly for a clear day and a sunny day. So this is a clear day, and this is how the system behaves. So you see here with the red line the PV production. The blue line is the state of charge of the capacitors. And this is the motor of the system. And you see that the state of charge at the beginning of the day is low, something like 20%. So then the available solar energy charges the capacitors, but there is enough energy here to start the system to operate and produce water. So you see that it has started producing water, the system operates. At the same time, the capacitors are charged until 100%. And then we have similar situation at the end of the day as in the beginning of the day, because you operate the system for some time until the minimum state of charge, which was set to 20%. And this is the product flow, the freshwater flow, and the product conductivity. So you probably know that the conductivity of the produced water from the membranes, if the pressure is lower than the nominal one, the conductivity is higher than the nominal one. So usually the nominal conductivity is something like below 500 microsiemens per centimeter, and what you see here. But if the pressure is lower, then the conductivity, the salinity of the fresh water goes up. And this is also some additional results with the behavior of the vessels, but during that day, you see that the vessels didn't play any role because everything was done by the capacitor. Now, for a cloudy day, you have these variations in the solar radiation intensity. And what you see here is with the green line, which is the motor, you see that the motor here is stopped. Stopped, because there is not enough power to operate the system, or the control system decides not to operate the motor, but to use energy from the stored energy, either from the vessels or from the capacitors. And as you see here now, the product flow is this. You see there is some fluctuation here, but there is production, although the motor is not operating. And this is the variation of the conductivity, which is, okay, it is within, let's say, acceptable limits during the daytime. So it produces water that can be potable. And now you see that in this case, there is some energy provided by the vessels and the red line. And what about the energy consumption? You see it's quite high for this small system, well, this was expected. So during a clear day, you have production of something like 550 liters, while during the cloudy day, of course, lower. But the energy consumption is, we see, very close to each other during these 2 days. And that's the energy consumption by the. So the conclusion from this project is that the incorporation of a short-term storage for a direct connection system, for an autonomous system, and an intelligent control results in significant benefits. That is more water production than a simple direct connection of the system without storage. And it's also the very sub-pressure variations are reduced, which probably is beneficial for the membranes. And there is no intermittency in the system operation. That is, there is no zero production of water during the whole daytime, even during cloudy days. You still have water production, even small quantities. The next step is to consider incorporating a reverse osmosis system in a microgrid. So we have developed, there was a European project and we installed such a system in Egypt. So this is a wind generator here. It was a hybrid system and photovoltaics. And this is the two-phase grid that we supplied some power to some villages over there, some houses over there. And the system also included water production. So in the load, there was also a reverse osmosis system. And this is the layout of the system and the sizes of the different technologies. In this area, this is inland, somewhere 100 kilometers north-south of Alexandria, if I remember well. So there is a very large area there that can be used for agriculture or other development, but there is no water. And well, there is water, but you have to pump it, and it is brackish. So you need to desalinate if you want to use it for agriculture or for other purposes. And these are the batteries of the system, the membrane, cartridges, here, filter, and the tanks for the fresh water. Now, we have developed a special control system, or Mr. Karavas at that time was part of his PhD. And you see the layout of the system, and this is the energy management system. This work is now being continued by Vasilis. And as you see, according to the calculations, and that were tested partially experimentally in that system, you may have water stored during the whole period of the year, along with providing electricity to other loads. So the control system, the purpose of the control system was to provide electricity and water through this microgrid to the people or to a community that wants to have power and water. So the conclusions were that the desalination is an attractive means of storing energy in the form of water. It offers possibilities of increasing renewable power penetration in weak autonomous grids, such as those of the islands. And excess electricity produced by renewable energy can be used to desalinate water. So that's the idea, is to use then in microgrids or in larger grids, the water as a means of storing water. And with the smart energy management system, you can operate the desalination unit at variable load. You can achieve load shifting, and you can also assist to any problems of frequency stability by using the desalination unit at operating it at variable load. In addition to these trials, we've been testing membranes theoretically and do some calculations and also some tests. Vangelis is doing this work. He mentioned a few things during his presentation. So he's developed a model to predict if there will be any scaling on the membrane. Scaling and for reverse osmosis means probably you have salt deposition on the membrane that probably blocks the freshwater production, reduce the freshwater production. And according to the calculations Vangelis has done, it seems there will be some effect. This is not yet really proved, if I'm correct. I mean, there are some other groups that work on these issues. This has not been proven yet, but anyway, we have to check on that. And we also testing the possible influence of feed water temperature on the reverse osmosis performance. Why? Because as I mentioned, desalination is now implemented in cold areas in the world where the seawater can go down to 5 degrees or even less, if I remember well. In that case, you see that there is a strong influence of the water temperature on the reverse osmosis performance. For example, you see here that the specific energy consumption is quite higher when the water is cold, lower than 20 degrees, goes up, while after, if you are over 20 degrees, then it's okay, it's quite low. And there is also influence, the temperature influence also the productivity of the system. So after all these investigations we have done and following the study for the bank, we concluded that today, according to the technologies available, we can have these three options. We can choose one of these three options according to the local conditions for supplying power of combining renewable energy with reverse osmosis desalination. So the autonomous technology that we have been discussing already, the RO system is powered exclusively from renewable energy system, either through direct connection, but without energy storage, maybe with a small storage, and with a full battery array to support the operation of the system, probably even for 24 hours a day. But this is cost. This has a considerably high cost today because mainly of the cost of the batteries. In the semi-autonomous topology, the RO system may be powered by the renewable energy system, equipped with a battery storage, but surpluses of energy may be supplied to the grid. You can sell electricity to the grid, or shredded if the grid cannot absorb it, and the batteries are full, but it depends on the design of the system. And any additional battery power required by the reverse osmosis system may be taken from the grid. If you need to produce water, there is no power available, you just buy electricity from the grid. And the independent topology, which is the topology that has already been applied, both for photovoltaics and wind, where the RE system is grid connected. There's no physical connection of the renewable energy system with the desalination system, but the energy produced by the renewable energy system is meant to satisfy the energy required, the power and the energy required by the reverse osmosis system. So you buy and sell electricity, and this electricity is actually used for the RO plant. I don't know if I'm already late. Just a couple of slides about the cost today. The cost of water. You see that the size of the system does influence the cost of the produced fresh water. So the smaller the system, as you remember, I mentioned something like about 2,000, 3,000, 5,000 cubic meters a day. So we are here. While for larger systems, the cost is now about $0.50 or €0.50 per cubic meter, even less in very large systems, depending also on the cost of electricity. From an earlier study in 2015, you see that this topology seemed to be at that time the most beneficial one. And actually, from what we calculated just a couple of years ago, you see that this topology, the so-called independent, I called it before, so this, in fact, this net metering, has now quite impressive, but this is for the conditions in the market of Greece. Okay, this is done. We took into account the cost of electricity in Greece and so forth. So you see that this, although even these topologies produce water at quite low cost. So it is feasible to apply today, implement renewable energy reverse osmosis systems. And this is a commercial case from Milos Island in Greece, where you have the reverse osmosis system. The capacity is something like 3,360 cubic meters per day. The electricity is provided by wind generators, two actually, of total 600 kilowatts in this island, small island. It receives many visitors during the summertime. The water was not enough. And the investor decided to install 2 additional wind turbines to satisfy the energy required by the plant, although the local grid was already full. I mean that it could not accept, when you have an island grid, there is only a small percentage of renewable energy that we can install because of the safety of the grid. So this was already full. It was saturated, but it was allowed by the grid operator to install additional wind turbines just to satisfy the additional electricity required by the reverse osmosis system. And if there is more energy produced by these 2 additional wind turbines, this is shredded, cannot be absorbed by the grid during winter time, for example, while the other time it produces electricity, and then the system uses the electricity from the grid, the reverse osmosis system, to produce fresh water. The investor sells the water to the municipality at a reasonable price. The visitors and the people get fresh water, and everybody's happy. The municipality sells the water a little bit higher, makes some money, and that's a very successful investment project in Milos Island. And as I know, larger systems have already been installed in the Emirates with large photovoltaic systems with a net metering topology. We're going to investigate short-term energy storage now using the lithium-ion batteries. And of course, Vangelis is going to continue his investigation with these special cells of the membranes to see what will happen to the membranes if we have variable operating, long-term variable operating, to see if there will be any effect. Thank you very much.